Good afternoon, everyone, and thanks for coming to my talk today. This is a talk on domain adaptation, and the title of the talk is Latent Domain Phrase-Based Model for Adaptation. And this is the joint work of my advisor, Khalil, and I, and we also want to give a thanks to Ivan, I'm glad that he's my second supervisor now. And also I want to thank Gideon for a lot of technical help. Okay, so let's get started. Nowadays, one nice thing with doing research in statistical visualization is that it's pretty easy to download bilingual data. For example, from Europa, from United Nations, from Common Crawl, and so on. But the point is that the data we use can come from various domains and resources. And how does it affect a phrase-based system when we train on such kind of data? And this is what I do focus on right now. And what I found in practice is that bigger data, is different to better. It doesn't always mean that better system performance, and I think this is not new. And a lot of previous work about data selection also mentioned about this point. So the point is that why does this happen? This is what we are really interested in, and to exemplify the phenomenon, we do some experiments. And I think this is kind of cool experiments when we train some phrase-based system on really large and mix of domain data, which include Europa and Common Crawl, United Nations, news, commentary, software, and hardware. The point is that we just try to collect the data and then combine them together, and then we learn very large phrase tables with roughly 100 million phrase entry, 200 million, or even 300 million entries. And then in the end, we test the system on a really specific test set related to electronics and to see what happens. And some of you might attend my talk at Khalil might be familiar with these examples. And I think it's really interesting. I mean, for example, here when we train a system on 1 million parallel sensing, and then we, in the end, we test it on a Spanish sensing like an input. And what we got in the output is that you can see here the point is translated to me quite good to commence with file rather than to open it with file, or password teacher rather than master password. And the point is why did it happen? It turned out that because in the mixed data it contains kind of relevant and irrelevant translations. For example, for the word maestra in Spanish here can translate to master when it comes to computer. It also can be translated to teacher when the domains of data is the education or even the dean and correct and so on. The point is that we want to confirm the result, so we double the training data to 2 million parallel senses to see what happens, and it turns out the story still goes in the same way. I mean, it still translates something quite weird, like you see here, the player can reproduce size of audio rather than can play back audio signal with the same reason. That is, for example, the word reproduce is in Spanish. It can translate to reproduce when it comes to science, or playback when it comes to electronics, or render when it comes to software. And we double training data to 4 million parallel sensing, and it's still the same. Some quite all avenues rather than outdex. So the point is, this is the problem with what we induced a kind of domain confused statistics, which means that the statistics that reflects the transition preference average diverse domains. And the point is that this is also the challenge, how we can learn the domain-focused statistic, which means that statistics that induced with respect to the target task, and we can use in-domain data as prices to do that. And to illustrate the challenge, you can see the picture here where the red curve can be represented domain confused statistic. And you can see here that, for example, we have a phrase F, and there are too many possible options. And look at the curve. We cannot know that which one is the best option. And the point is that the option, the transition options that are relevant to the stack, it's it doesn't mean that it's the best in terms of transition probabilities. So the challenge is how we can learn the kind of domain-focused statistic, which, as you see here, is not flat anymore. It's really sharpened, and we can easily find out that which one is the best transition with respect to the task. And how we can learn this kind of statistic, we name this kind of training like in-domain corpus-focused training. So I will go in detail how we can do this. The first point is that we introduce the latent domain variable, which we usually use the word D to represent domains of data. And we use D1 to represent that, okay, this is in-domain data, this is what we need to induce. And we have to induce 0, like irrelevant domains. The point is, we don't really care about irrelevant domains, but in the end, we still need to induce them to learn D1. Like, for example, we need negative examples to learn positive examples, something like that. That's the point. So with the introduction of latent domain variable, what can we do? We can learn the statistic with respect to the latent domains. In this work, we present how we can learn phrase transition statistic with respect to D. For example, for a phrase here, we learn P of phrase E given phrase F with respect to D. And the point is that we saw that, okay, we can also learn the lexical weight statistic with respect to D and reordering statistic with respect to these. And in this talk, I will present in detail about how we can derive such kind of statistic with phrase transition statistic with respect to this. And for about the lexical weight and reordering, you can find out on our paper. So what is the contribution of the domain-focused statistics? Remember that in domain adaptation, we usually have the in-domain data and mixed domain data, and the normal approach is that we train two systems. The first system is on the in-domain data, and the second system is on the mixed domain data. And but somehow they disconnect to each other. I mean, in the literature, the way the people do it is just try to combine them together, like the combination system. And this work can be kind of can do a complementary contribution to the DA literature. Kind of the statistic can be used as additional feature to improve the mix of domain data using in-domain as price. But in fact, we are interested is how we can use the statistic to replace the former, the baseline, rather than the additional feature, because we think that it's much more fun to do that. So now we come, now I will present in details how we can learn the statistic with respect to D. Here, P of phrase E given phrase F and D. And the point is that it's really natural is one comes up with the idea of using AM for this kind of distribution. But remember that when we play with EM as the phrase levels, we have to be really carefully. We need the kind of fancy model to do that. I mean, it's not trivial, I have to say that. So the point is that in order to simplify the problem, we found that a simple decomposition really works. Like we decomposed P of phrase E given phrase F and D proportion to P of phrase E given phrase F and P of D given phrase E and phrase F. And for the first factor, it's really easy to estimate it. We just use relative frequencies to estimate it. But for the second thing, this is the cool thing. We can use expectation maximization to learn it. Before we devise in detail the learning algorithm that's presented in detail here, there are two kinds of D. So when we have PD1 given phrase, it's model how relevant a phrase pair, and for D0 given phrase, we model how irrelevant a phrase pair. So now I will present a demonstration of EM learning framework for PD given phrase. The point is that how we can learn PD given phrase, we can embed the probabilities into phrase transition probability. Like you can see here, you can see you PD given phrase, you can update PD given sensei, and then you PD sensei to re-update PD phrase. It's pretty straightforward and simple. And in two steps, the first step is you PD given phrase, update PD given sensei. It's not easy, I have to say that. But for this, another step, PD given sensei, update PD given phrase is pretty straightforward. We just use PD given sensei to to softly fill in the value of D and then estimate PD given phrase. Okay, so what's the next? The next is how we can define PD given sensei in a nice way, which we can use PD phrase to update PD sensei. To define a PD given sensei using Bayes rules, we can decompose it into components. The first component is a generative process of the data given the domain data, given the domain, and the second thing is the domain prior. And no, it's obvious that it's pretty easy to estimate prior. It's just summarize all the PD given phrase. But the point is how can design a generative process for sensei given domain? And our generative process is really simple. We can use D to generative E first, and then both D and E can generate F. And the other option is that we can use D to generate F first, and from both D and F we can generate E. To model this kind of thing, we need 4 components. The first component is how we can generate E from D, like the probability of E given D is really easy. It's kind of language model. We just train this kind of data, and then we can estimate it. And it's similar to from D given F, it's kind of language model. But the point is that for both D and F, how we can generate E, it turns out that it's not trivial. Or from D and F, how we can generate E is not trivial. So our solution is that we simplify the transition model to kind of the multiplication of all the possible phrases we can learn from the sensei. Here you can see that P of sentence F given sentence E with respect to D can be estimated by multiplication of all the possible phrases, P of phrase F given phrase C and D, and so on. So we now have a full learning framework. Let me explain it again. We can use PD given phrase, and then from PD given phrase, you can estimate P of phrase E given the phrase F and D, and we can estimate P of phrase F given phrase E and D. And then from P of phrase E given phrase F and D, we can update P of sentence F given sentence E given sentence F and D, and so on. And from the sentence transition probabilities with respect to D, we can combine with the language model to define how we can generate the data P of sentence E and sentence F given D, and in the end we can estimate the PD given phrase, which is use PD given phrase, update PD given sentence, and then from PD sentence we can re-update PD phrase. It's pretty simple. The last important point is how we can start the training producer. It's really simple. We can train a phrase-based system on in-domain data, and we can assume that this is the phrase transition probability with respect to D1. And we can train phrase on the mix of domain data, and we can assume that, this is the P given phrase with respect to D0. Now we turn to experiments. In fact, there are a lot of interesting questions, so I will present 2 most important questions. Some of them, at least for me, I think it's 2 most important questions. And all the results can be found in the paper. So the first question is how the domain-focused statistic with respect to D1 can replace the former. And the second question is how many iterations needed to train the framework. And all the results can be found in the paper, like how can adapt lexical waste, how we can adapt reordering models, and the result on various adaptation tasks, and how our research complementary contributes to a full domain adaptation system. Okay, for data preparation, we train on a mix of domain data from 1 million, 2 million, and 4 million parallel sensors, combine a lot of data from a lot of domains and resources. And we use an in-domain data set with, for example, 100K in-domain sensing pairs, and the domain is Toast electronics. And here you can see that when we use domain-focused statistic to replace the domain-confused statistic, we achieve kind of significant improvement. And the point, the really interesting point, is that when we increase the training data to larger and larger, we observe that we obtain a better improvement. It's really interesting, I think. But in the end, the numbers are just a number. So how does the improvement come from? We can take an example here when we translate an input, reproduce Spanish input, and the baseline is translated something quite weird. Can reproduce sign of audio, but when we use domain focused statistic to replace the domain confused statistic, it translates something more reasonable. Can play signals audio. And when we look at the detail of the phrase table to see what happens, and it turns out that as we analyze the domain confused statistic, the transition probabilities is quite equal, and it's really, really hard to determine which one is the best option. But when we look at the domain focused statistic, we can easily recognize that, okay, for the word Spanish, signals, I don't know how to say this correctly, it can translate to signals in a clear way and similar to other examples. And the second question is how many training iteration we need to train the model. But it turned out that you see, there's no really correlation, strong correlation between the blue score and the number of training iterations. What EM does is try to minimize the entropy of the phase transition probability without doing care about the phase transition, about the performance of the system. Okay, so final discussion. Why is the derived domain focused statistic works better? The point is that when we decompose it in this way, and when we can learn PD given phrase, when the estimation is reliable, so we will have a really meaningful phrase transition probability with respect to D. But when PD given phrase is not reliable, it means that phrases are rare. So when phrases are rare, we found that the phrase transition probability with respect to D will approach to 1, and the baseline is also approach to 1. So by somehow they are kind of equally informative. So at least you can see that when we use domain focused statistic, it's at least equal or even better than the baseline. But we still have challenge, like I said. I mean, EM, what EM does is try to sharpen the PD given phrase, and it tries to do it without taking care that whether it's good or not. It's quite sad, but it's true. And in some cases, even not so often, we found that performance can significantly drop at the iteration 2, and how we can avoid this. So we hypothesize that backup models can help. And also a challenge that how we can define a generative process. Let's see, because the transition model with respect to D is too hard, and we simplified it in this way, and we found that, okay, this is too naive transition models, but by somehow it still works in a reasonable way. So, but in the end, we still think that, okay, we need to improve it. And the second question, I mean, the last challenge, how can generalize to domains, to end domains? I mean, by somehow, I did try a lot, but by somehow I personally did not achieve any so much improvement. And Khalil has some idea, and also Ivan has some ideas, and I hope I can improve it in future. Thank you.
So nice talk, and we have several minutes for questions, comments. No? Okay.
Hi, thanks. That was great work. I was wondering, have you actually done any comparisons with a different domain adaptation technique, like for example the data selection by Axelrod or whichever you like?
Yeah, in fact, in our previous work in this model, we use only for data selection in our coding paper, and it turns out that for the work of Axelrod, we just only used monolingual information. And for this kind of framework, you can see that we use not only monolingual information, but also transition mode information. And we found that in our previous work in coding is outperformed the baseline.
All right, and for your experiments, the language model, was that already adapted, or was it just a...
You mean alignment model?
No, the language model, was it adapted to the domain, or was it just...
Sadly, no.
Okay, thanks.
Yeah, but I think it's a good suggestion.
Thanks for the talk. So I'm wondering to know if the size of in-domain data, how many in-domain data we need to improve using your technique.
Well, it's a good question. I mean, in fact, in our EMIP paper, we tested on 6 or 7 in-domain tasks with different in-domain data size, and we found that the result improvement is not really consistent with the size of the in-domain data. It's really consistent with the relation between the mix of domain corpus and the in-domain corpus we used. You get my point? It's really, yeah. It's funny that in our experiments, when we use in-domain corpus with only 22K of parallel sensing, we achieve the best performance of the improvements. It's quite weird, but yeah.
I have a question. So, I think that I believe that your phrases are extracted based on word alignment. Is that correct? And is there any influence by the word alignment? Because the word alignment itself is not domain adapted in this case.
Yeah, it's true. Yeah. We in fact have some plans for doing research in word alignment, how we can adapt alignment, and how we could come up with some. Hope so.
So I have another question, and I'm wondering because you are running EM algorithm, and there should be kind of degeneration problem favoring longer phrases preferred during the training. And do you have any? Did you observe such tendencies, or is that the reason why it didn't work for? You tried many alternatives for mixed domain, multiple number of domains, or different experiment. Do you think that might affect the problem? Or?
Can you ask the question again?
The degeneration problem, because the longer phrases will be preferred during EM algorithm. You mean that a higher probability mass will be assigned to a longer phrase pairs?
You mean this point? When the PD given phrases just decrease?
Yeah, longer phrases will be preferred, and probably shorter phrases will be ignored during training.
Yeah, that's the point. I mean, what EM does is try to sharpen the PD given phrase. So, yeah, you're right. That's the point. In fact, it's really hard. This problem, I think, is general. I mean, because the correlation between the likelihood and the desired things we want is not so tight. So, yeah.
You're referring to the generative behavior of EM on full phrase-based systems if you train the phrase table under EM. Well, this is the thing that Hoang had in one of the slides where he fixes the probabilities, the conditional probabilities of the phrases, and he's training only the D given the phrase pair, which basically avoids the problem of overfitting longer and shorter phrases. Okay, so yeah.
Any questions, comments on the? Okay, great.
Thank you.
Thank our speaker again.